Welcome back. This is Mr. Hassan's Maths channel. I'm now answering question number 7 from the specimen paper of the Cambridge 9709 paper 4. This is the mechanics paper, and this is the specimen paper for post 2020 exams. And the question here tells us about these two particles A and B, mass is 0.8 kilograms and 0.2 kilograms, which are connected by a light inextensible string. Particle A is placed on a horizontal surface. The string passes over a small smooth pulley P fixed at the edge of the surface, and B hangs freely. The horizontal section of the string AP is of length 2.5 meters, and the particles are released from rest with both sections of the string taut. Given that the surface is smooth, find the time taken for A to reach the pulley. So here we have a situation where we have a smooth pulley, right? So, and a smooth surface. So there's no friction in this situation. So if we look at the forces acting on A and B, the forces acting on A and B are their weights. Okay, for A and B, their weights, and the tension in the string. And that's all. Okay, so for A, you'll have a tension acting this way. It's going to be pulled by the string that way. And B, you're going to have a tension in this way. It's going to be pulled up. Their weights, A has a mass of 0.8, so its weight will be 0.8 G. And B will have a mass of 0.2, so its weight will be 0.2 G. Okay, those are the only forces. There's no frictional forces acting on this system at all, and so those are the forces acting on these two. Now it's going to accelerate in this direction once it's released, and we need to find the time it takes for A to reach the pulley. Now it's going to be a constant acceleration, and this is going to accelerate this way, of course. It's going to be a constant acceleration, so we can use the Suvat equations to find T. But before we can use the Suvat equations, we have the displacement, how far they're going to move. We have the initial velocity. We don't have the final velocity. If we can find the acceleration, we can then find the time. So we need to find the acceleration. That's what we need to focus on. So what we can do is we can resolve the forces. We can consider A and B separately. So let's consider A first. Let's consider A. And the direction that it's going to move is this direction, according to the diagram. Okay, so I'm going to resolve forces in that direction. Now there's only one force acting on it, which is T. So the resultant force, so what we're using here is the resultant force is equal to the mass times the acceleration. So the resultant force for A is just T, and it's equal to the mass, which is 0.8, times the acceleration, which is A. All right, so that's one equation by considering A. Now if we consider B, if we consider the particle B, it's going to move downwards. It's going to move downwards, and it's going to have the same acceleration as A, and the tension throughout the whole string is the same. How do we know that? Because this is a light. It's a light string, meaning the tension all the way through the string is the same. There's a smooth pulley, meaning the tension on either side of the pulley is also going to be the same. And it's an inextensible string, meaning the acceleration of everything that's attached to this string will be the same. Okay, so the T and the A will be the same in both cases for A and B. So we have here, if we resolve taking down as positive, the resultant force will be 0.2 G minus the tension, and that's equal to, and that's going to be 0.2 times A, and that's the second equation. So we have these two equations, and we can solve these two equations simultaneously by either substitution or by just adding the two equations together, because T will be eliminated and we'll find what A is. If we add these two equations together, this side of the equation is like T minus, added T plus 0.2 G minus T. So the T minus T will become 0. You're left with 0.2 G on this side equals, and you have 0.8 A plus 0.2 A, which is going to be just 1A. So that's the value of A. Therefore, A is going to be 0.2 times 10, which is 2 meters per second squared. So now we found the acceleration, and we can now use the Suvat equations to work out the time it takes. So we know that this is going to move 2.5 meters. Both of them will move 2.5 meters, of course. So 2.5, U is going to be 0 because it was released from rest. V we don't know, we don't need to know, actually, we don't need that. A is 2, and T is what we have to find. So we have to have an equation involving S, U, A, and T. So if we look at equations, we have S equals UT plus a half AT squared. So we're going to find T, and we know all the other things here. So S is 2.5, U is 0, so 0 times T plus a half times 2 times T squared. So that becomes 0. So you're left with 2.5 equals, they cancel out, T squared. Therefore, T is equal to the square root of 2.5. And we only care about the positive square root. So we're going to take our calculator and we find the square root of 2.5. And that gives us our answer, which is 1.58. Okay, so 1.5811, 1.5811 seconds. So therefore, we can say the time is equal to 1.58 seconds to 3 SF. So there's the answer to part A. Okay, now for part B, it says it is given instead that the surface is rough and that the speed of A immediately before it reaches a pulley is V meters per second. The work done against friction as A moves from rest to the pulley is 2 joules. Use an energy method to find V. Okay, now we're going to use an energy method, right? So we're going to consider the total kinetic and potential energy of these particles as they're moving across. All right, so we can see that what's going to happen to B as A moves from here to here. A will end up over here at the pulley, and B will end up down here somewhere. Okay, let's draw it over here. B will end up over here at the end. Okay, and it's going to drop a distance of the same distance, of course, that A will be moving, 2.5 meters. Okay, so what I'm going to do is I'm going to consider this level here, because we're going to be dealing with potential energy and kinetic energy and so on, because we're using energy methods. I'll consider this level here as the potential energy being 0. All right, and for A we don't have to consider potential energy. We can call the potential energy for A 0 because it's going to be on the same level, but B will drop. Okay, and this is the start for A, and this is the end for A. This is the start for B, and this is the end for B. This is where B ends up, right? So there's a nice equation that we can use, which is really very useful in any question involving energy questions. And that is this equation that I'm going to show you now. And we're going to look at the total kinetic energy at the start plus the total potential energy at the start plus the work that went into the system is equal to the total kinetic energy at the end plus the total potential energy at the end plus the work that came out of the system. The work that went into the system is any thing that was like added to the system, like if something was pushed, for example. Okay, if there's a driving force, something being moved. Okay, and the work out is any type of work that took energy out of the system, like any resistive or frictional forces. Okay, so if we look at this, we can consider A and B separately. So let's look at the kinetic energy of A. Okay, at the start it's 0. Okay, so this is 0 for A and B. Okay, so we can say here the kinetic energy at the start for A is 0, and the kinetic energy at the start for B is also 0. They're both 0. So that part's 0. Now the potential energy, you got the potential energy at the start for A. Now I'm considering A along this line over here. Okay, its potential energy, it basically will be, it won't be any different from this point to that point. All right. So the potential energy of A is going to be, I can call it 0, right? But the potential energy of B, okay, at this point is going to be equal to the potential energy at the start of A. This is going to be equal to mgh. All right, so here it's going to have a potential energy, which is going to be, so for B, it's going to be the mass, which was, for B was 0.2. Okay, so this is mgh. Mgh, it's just weight times its height, the work done against gravity. So it's the mass, which is 0.2, times g, which is 10, times h, which is 2.5, plus the work in, which is 0. There's no work gone into the system. There's nothing pushing it or anything like that. It's just, gravitational forces, which is included in the potential energy. Then we say the kinetic energy at the end. So you're going to have a half times the mass of A. So it's going to be moving with the velocity here, v. Okay, so you have a half times the mass of A, which is 0.8, times v squared. Now they're going to have a common velocity. So this is also going to be moving with a common velocity here, okay, which is going to be plus a half times 0.2 times v squared, plus the potential energy of A and B will both be 0 because this is on the same level. All right, so whatever potential energy it had would cancel out from both these sides. So I'm just going to call it 0. Okay, and plus the work out, well, that's the work that came out of the system, which was the work done against friction, which is 2. So that's going to be 2 joules over here. Okay, so now we end up with this situation. We have 2 times 2.5, which is 5, is equal to, that's going to be 0.4 v squared plus 0.1 v squared plus 2. So we end up with 5 minus 2, which is 3, equals 0. That's 3 equals 0.5 v squared. That's right. Okay, so we divide both sides by 0.5. So 3 divided by 0.5 equals v squared. So 3 divided by half, which is 6. So v squared equals 6. Therefore, v is equal to the square root of 6. And we know that the square root of 6 is equal to 2.4494. 2.4494. So we're going to write this as v equals 2.45 meters per second. That is the velocity of the particle, particle A as well as the particle B before A reaches at the point where it reaches the pulley, when it's traveled 2.5 meters. Okay, so this is using an energy method, as they ask us to do, to find V. All right, so this is a nice little equation. The total kinetic energy of the whole system before and the total kinetic energy of the whole system, after, or plus the total kinetic energy before, plus the total potential energy before, plus the work that went into the system will always be equal to the total kinetic energy at the end, plus the total potential energy at the end, plus the work that came out of the system. That equation will help you to answer any type of energy question very easily. So work in is the work that went into the system. If there was a driving force, something being pushed along, all right? And the work out is always to do with the work that came out of the system, things like resistance and frictional forces, which reduce the energy in the system, okay? So work in increases the energy in the system, work out decreases the energy in the system, and that's how we dealt with this question, okay? So as I mentioned, although if I've called this potential area energy 0, I meant for B alone. For A, we don't need to consider the potential energy because the change in potential energy is going to be 0, right? So whatever value we got here for A and there for A would be the same. So when you subtract them, they'll give you 0 anyway, because it's on the same level. So we only really consider the potential energy for B. All right, so that's the answer to this question, and I think that's the end of the paper. Yep, that's it. So we've done the whole paper now. So this specimen paper, if you want to see other questions from this particular paper, you can find them in the playlist, which will be linked at the end of the video in this area over here. You click on that link, it will take you to the playlist for the whole of this paper. You have, you want to see questions about, I guess this is going to be under 2 topics. Part A is under dynamics and connected particles. Okay, and part B I'll put under work, energy, and power. So I'll save them in this question in both of those playlists. And if you want to subscribe to my channel, click on this link. And the card at the top of the video takes you to another video which tells you how to use my channel in an efficient manner. Thank you for watching and see you soon.